So it's my great pleasure to introduce my friend and fellow member of the CARC-RACS contesting team, Professor Alwyn Seeds, G8DOH, who is going to talk to us about building a VHF-UHF contest station. Success in VHF-UHF contests requires three things: a good site, skilled operators, and a high-performance contest station. In this talk, Alwyn will describe key considerations in building a high-performance contest station for the VHF-UHF bands, including a choice of aerials, receive system designed to maximise dynamic range, and transmit system designed to give a clean signal which meets the requirements of the RSGB VHF-UHF Code of Conduct, or Code of Practice. Both of them may be applicable. Alwyn G8DOH was first licensed in 1970 and has been active in contesting on the VHF and UHF bands ever since, starting with a few watts of AM on a modified Pi Ranger on 2 meters and moving through FM from a single 4CX250 to current LDMOS amplifiers and multi-array systems. He can be heard on the bands either from his home QTH in North Oxfordshire from IO92 or from JO01 with the Crawley and Reigate contest group, Golf 3 Mexico and Golf 5 Lima Kilo Portable. Said that a few times. Professionally, he works on microwaves and terahertz systems and founded the wireless company Zinwave. Alwyn, thank you.
Thank you very much, Stuart. So, let's see if we can get it to click. That's the first thing. Yeah, so first, what's in the talk? I think the first thing, and it's a really important thing, is the RF environment in which we have to work. Then really working through the system. Aerials, receivers, transmitters, and conclusion. But in terms of the scope, I'm going to talk about some of the issues that matter and give some measurements and examples. I'm only talking about terrestrial contesting. For EME, it's quite different. And in particular, you don't tend to have as many problems with really loud, unwanted signals, but you have a lot of problems in having low enough noise and good enough sensitivity. So it's a different type of operation. And the other thing is, as the abstract said, you need a good site, good operators, and plus the station. And there's nothing in this talk about choosing sites, the vital role of IT, or indeed operating, because those things are subjects for a talk in themselves. And finally, I don't have any involvement in any manufacturer or dealer of amateur radio equipment, so what I say about different products is just my observations on them, and it can be taken as one person's opinion. So let's talk about the RF environment first, because I think that perhaps not enough attention is paid to this. I always find people are trying to get ultra good low noise amplifiers anchored on the back of the antenna on every band, and frankly I don't really understand why, because at 6 meters the noise temperature, and this is the minimum temperature you'll get if you beam horizontally, is a good 10 dB above what you get out of a 50 ohm load. You have no need of an extreme low noise figure receiver. And by making an extreme low noise figure receiver, what you'll do is you'll make yourself very prone to overload. 4 meters is still quite noisy, but less so. 2 meters is the magic sort of transition point where you're about at the received noise level that you'd get from a 50 ohm load. And then 70 centimeters is a bit quieter, 23 sems is quite a lot quieter. And then as you go up into the microwave bands, it's quieter still. So the sensitivity you require depends on the band you're on, and you need to pay attention to this point, because every time you improve the sensitivity, you make the strong signal performance worse, so there is a compromise. Also, these are the minimum values you can get. In practice, most sites are more noisy than that. In UK rural locations, the noise floor is frequently up to 10 dBs higher, and in urban areas, we could almost run the light bulbs off the directly off the antenna and hence save energy. I've measured more than 40 dB above these levels in central London, for example. So what we need to achieve is that receivers should be less noisy than our level of received noise, and importantly, the transmitters we deploy should not actually raise the noise floor, because if you do that, you're just making life miserable for every other contester, and okay, it means in aggregate we'll all work less stations and we won't work as much DX, which is a bit disappointing. So transmitters matter. Right, now on to the strong signals. This is free space path loss equation, which tells you unsurprisingly that the loss goes up the further you are away, D, and the higher the frequency, because the signal spreads out, the area covered is larger relative to the mechanical dimension. So that's the basic formula, and the amount of loss you get, around about 100 dBs, 2 meters and 70 centimeters. If the path hits the ground from time to time on the way, so we're talking about strong signals and hence short paths, you can increase the loss by 10 to 30 dB. If you have a beautiful piece of water optimally placed, like a nice lake, you might be able to enhance the signal. It can go either way, but on typical undulating ground, you usually end up with a loss relative to free space. So, what's the implication? We now add on the other bit, which is aerials, transmit and receive. So the receive power is the transmit power. This is a sum done in dBs, hence no multiplications. Transmit power plus the gain of the transmit antenna minus the propagation loss plus the gain of the received antenna. So what tends to happen is, as we go to higher frequencies, within mechanical constraints, we can make a bigger aerial. And if you did just directly scale so that the aperture of the aerial was growing, you had the same mechanical aperture at all the times, you would end up with received powers rising as frequency squared. Well, we don't actually build antennas of that size generally, so we don't usually achieve that. But taking now some examples of practical aerials, these are the sorts of things you might use. What you see is that your strong signal problems tend to get really alarming by the time you get to 2 meters, and 70 centimeters a little bit worse. 23 centimeters, well, it should be getting worse still, but in practice people don't build large enough antennas. Some do, but the average doesn't go up quite as steeply. So this is quite interesting in terms of the strong signal problems that we have. 2 meters and 70 sems tend to be really difficult bands for strong signal problems. So that's the other bit we have to take account of in design. So here's a measurement. This is 2 meters, 2 stations running high power. The spacing between the stations is just over 16 kilometers, and these are measured results. So in theory, you should get a received power in the measurement bandwidth here of about minus 40 dBm. That's 0 dBm is a milliwatt, so minus 10 is a tenth of a milliwatt, hundredth of a milliwatt, and so on and so forth. So you should get a received signal of about minus 40 dBm. In this measurement, we actually got minus 44. So not much scatter loss. It's a nearly free space path, but not quite. That is a strong signal. You need good receivers, and that just illustrates 16 kilometer spacing. Go closer, it gets harder. And the other thing I should have said about that slide, which I didn't mention, was this little factor. This was measured when the distant station was beaming exactly in the opposite direction. So I had the benefit of 24 dB's front to back ratio on their antenna system. When they rotated the antenna to go my way, that just went off the limit of what I would handle in the A to D here. It exceeded minus 25 dBm. That was really strong. So it shows it's a real practical problem. The thing people give a bit less attention to, because they don't hear it so directly, is the problem of out-of-band signals. So, you know, these are 2 meter Yagis, designed for 2 meters, but just look at what they pick up at other frequencies. So this is an example. It's rural Oxfordshire, but I have more than neg 30, about minus 28 dBm of FM. I have DAB. I have a local Tetra transmitter. That's just down the road. Going up a bit, I have DTV. I also had cellular, which was distant because it was rural. But now, as part of the ESN upgrade, I now have a cellular system which is 100 meters away. These broadcast signals here, here, and here are from the Oxford transmitter, which is 33.5 kilometers away. So these are big signals, and basically for things to work properly you need to get rid of them. And at our contest site we happen to be not 33.5 kilometers, but we happen to be 500 meters away from a main FM, DAB and Tetra station. So you actually get on FM at 500 meters from that one, you get 0 dBm, you get a milliwatt of FM. Ordinary boxes don't like that very much. So, now on to the issue of aerials, the first choice you've got to make. People in contests, especially 24-hour contests, come and go because not everybody is enthusiastic enough to be there for 24 hours. So for you as a contest station, so that you can work them all, you need to be loud, and you need to be loud with as many stations as possible, and you also need to be there all the time. That way, anybody who pops on, they see, oh yes, there's a great big signal there. Oh, there is a psychological propensity in radio amateurs always to work the strong signal first. And that's very handy. So, you've got to be loud. You've got to be loud around the azimuth, and you've got to be there all the time. But then on receive, you've got to find from that whole azimuth of stations, you've got to find stations quickly, and also, if you've got strong other contest stations nearby, you've got to minimize the strong signal effects from them, otherwise you won't be able to work the weaker stations. So, what are your choices? Well, basically, since you're trying to work quite distant stations as well, you want to get as much power as possible close to the horizon, rather than up into space or down into the ground. And there is actually a simple practical limitation on that. You can't restrict the vertical beam width to nothing, because we use masts, and masts blow around in the wind, and unless you're into very serious mechanical engineering, I don't think you can reliably achieve correct support of an antenna with a vertical beam width less than 5 degrees. Now, for the microwave people, of course, you do much tighter than that, but you make a compromise and you keep things close to the ground, you stabilize them very carefully. But for the VHF people, you need to accept that limitation or go in, as I said, serious mechanical engineering. But it's the first way of increasing your loudness and putting your power where you need. So, but then all the choices start. Here's my first example. A couple of 15-element LFAs. It'll give you 19 plus dB dBi and a horizontal beam width of 28 degrees. The vertical beam width's not that efficient. It's only 15 degrees, so you could ideally, if you had a little stack of maybe half a dozen, you would do better. But that's a bit mechanically difficult to arrange, so you're on compromises again. But the important point is the bottom is the, let's just go back, the bottom number. It only covers 8 degrees in azimuth. So the people who are in the remaining 352 degrees don't hear you very well, and therefore you will find less stations. You will miss people. So how about this one? This is 4 times 7s stacked vertically. The gain is just a shade less. It's essentially comparable. But we've reduced the vertical beam width to 12 degrees and increased the azimuth coverage. This generally is more productive, and it's mechanically handleable, as you can see from the photo. We can take this a step further. This is a stack of 6 times 4 element LFAs again. Gains a little bit less, but we're still within 2 dBs of our stack of 15s. Smallish vertical beam width, 14 degrees, but I'm now covering 16% azimuth coverage. So I'm getting the percentage cover up. And of course, the next thing you do is you have lots of them. But you might be entering a contest under the 100-watt single aerial rule. So what do you do then? Well, most people buy a very nice aerial which is very efficient and pushes all the power out nicely, such as an LFA. All the side lobes of this aerial are better than minus 24 dB. So where you point at, you're very loud. You're not very loud anywhere else. Now, that's great, but for contesting, how about this one? This is a professional, same size beam, 8 element. It's a professional one. It's because it was designed to be wideband, and also because it was designed years ago, they weren't very bothered about side lobes. They wanted them to be fairly small so as not to waste power, but they didn't want them to be state-of-the-art. So the professional one has side lobes at minus 12 dB. Now I use a couple of these in North Oxfordshire, and the advantage is that, okay, I'm not loud on the side lobes, but I hear people calling me from all round the compass, and if they are rather quiet, I can turn the aerial round. But again, it gives me about 50 degrees of coverage at high, on the peak, but I get lots of calls from other bits of the compass, and that's useful just for finding more people. So so my message from this is, if you are restricted to a single antenna, think carefully about the compromises you want to make. The compromise of having not very good side lobes actually in forward gain has cost only 0.8 of a dB. It's a very small compromise because they're still quite low-level sidebands. They're just not ultra-low. So you can make this compromise, and it may enable you to work more stations if you're a single aerial station. Right, now let's go to the other extreme. Take a look at this one. I really like this. This is F8KGU, who I'm sure you've heard on many occasions. And KGU have a very nice setup because they've got an old French PTT microwave station. We use optical fibre now, so we don't need microwave stations much. So they've managed to get their hands on an old one. And it was from the days when we were doing capacity increases in microwave point-to-point, just the last ones were done in the early 1980s. So this wasn't enough, so they built a tower beside it, a tower so stiff it can take microwave dishes, lots of them. And there's a nice, if you're not vertiginous, you can just hop across on the feeder tray there, a quite high level. So what have they done with it? Well, what they've done is that on here you can see these stacks of 8-element Yagis. They have 8 times 8 elements stacked vertically. You see, the narrow vertical beam width, lots of power to the horizon, and a width of about 45 degrees for each of them. They've got 3 sets on there, different points of the compass. Then up here, on this little tower, they've got stacks of 4 times 8 element, a further 2 in other useful directions. They're over on the west coast of France, so they've got a lot of Atlantic, which isn't very interesting. Their choice, their vertical beam width down to either 6 degrees or 12 degrees, so it's really efficient use of power. And just the fixed arrays give them 64% azimuth coverage. So they've actually covered most of the compass that they want. And just to be on the safe side, they've got an 11-element rotatable on the top and also a big wheel. So they're not going to miss anyone on any azimuth except when they're working a different station. That's quite a system. Then the other one is an even more interesting thing in terms of design, which is DR9A, who we've all heard. Now DR9A's array is particularly neat because what they've done, they're following the same principles. They've got stacks of 6 elements, so they compress the vertical beam width, but they've got a lot of trees around them, so they can only have 1 mast, and it's a big one. And so what they have is they have 8 of these stacks going round the mast, as you see. The geometry gets a bit tricky to interleave them all. And so actually they have 360 degrees coverage, which they need because they're in sort of middle Germany, so they've got loads of stations every direction. But the thing that's interesting is, I said at the top, it's a phased array. So it transmits omnidirectionally, so everybody's going to hear them. But on receive, they can select the amount they want from each stack. So you have a little spin wheel, and you just electronically go round, and you focus your attention on roughly a 45-degree width. And it is literally just spin and check for people calling you. You can only do that perfectly, with good patterns, if you bring the antennas close enough together. The systems where you've got spaced arrays, different masts, the sort of thing that we use in G3M, you can't actually synthesize that beautiful pattern. It's not ideal, but nonetheless we get plenty of azimuth coverage, which is what we need. So that's an example of a rather elaborate system. Now, the microwavers, and I'll go up to 23 centimetres, have a problem because you've got to get, I said that you would actually need to scale mechanically in order to reduce the path loss at high frequencies. So in practice, we never quite get there. And so this is a 23 cem array. It's 8 times 21 elements. And you'll see as a consequence, whilst there's lots of horizontal gain, 23 dBs, and this one does give you 5.5 degrees, so that's on the mechanical limit vertical, so it's efficient. But the sad thing is it only covers 3% of azimuth. And that's why you spend your life on KST when you go to the higher bands. But of course, in the ideal world, if money was no object and time was no object, you could build a system with lots and lots of these to get more azimuth coverage. It just depends how much building you can do. But I just wanted to make the point that as you go up into the microwave region, you get much more dependent on, not achieving 360-degree coverage. You do what you can, but since it's often you're working stations of quite low power rather than maximum power, you may be struggling to find weak signals, and so you have to compromise and do your keyboard tapping to find the stations. And that's why the number of contacts on the microwave bands tends to be rather lower than at lower frequencies. Right, onto receivers and transmitters. I've already talked about out-of-band signals, and the solution is good filtering. And for in-band signals, to solve them, we need good systems design. So first of all, out-of-band, you need a good bandpass filter. This is an OCI one. It's a really beautiful thing. The in-band loss penalty is just 0.7 of a dB, so you can still get low noise figure on 2 meters, no problem. But even if you just go down to 140 megahertz, you've removed 30 dB of unwanted signal, and by the time you're at 132 megahertz, it's 60 dB. So you just remove the stuff, the out-of-band stuff that you don't want. You need those. So for in-band, we can't do that generally, so we have to somehow get ourselves a wide, spurious free dynamic range. And practically speaking, ideally, you could make use of 120 dBs of spurious free dynamic range, normalized to 500 hertz bandwidth, if you could get it. But actually, technically, we can't. But being close to 100 dB is very desirable. So the spurious free dynamic range is the gap between the noise floor and the time when an unwanted signal, a distortion signal, first comes out of the noise. So that's what we're trying to maximize. In hybrid receiver architectures, you have some sort of narrowband filter before going to the analog to digital converter, and so the performance is set by filter performance, mixer performance. And that gives you the dynamic range limit of such designs. If you have a software-defined architecture, then you don't have narrow bandpass filter, so everything depends on the performance of your analog to digital converter. So you've got rid of the need for a high-performance mixer and crystal filter, because you're going to do your filtering in DSP. You can do all sorts of lovely displays with it, but everything depends on this. And good quality ADCs, as the radar people know, cost lots of money. So here are some measured, this is data I measured, on the 9700, which has a software-defined receiver, but they don't have a dithering system that really works on receive. So different reviewers have chosen different levels of spurious free dynamic range. So ARRL decided that the that this was the point at which the distortion was coming out of the noise, which is true, but the distortion's also coming out of the noise here, here, various points along this curve. So AB4OJ was a little bit more exacting. He decided that the distortion was appearing here. Sherwood was a little bit more brutal still, and he decided that this was the point. And I'm really mean. So far as I'm concerned, if I can measure the signal coming out of the noise, that is the spurious free dynamic range limit, and I say that my 9700 has a spurious free dynamic range of 63 dB in 500 Hertz. I've also measured a good transverter with a case in 3A, which is this red curve, and it is the case, and I measured it, that that's the point where it comes out of the noise, and I have 99 dBs SFDR measured. So for transceivers in a box, the IC9100 remains one of the best ones, although it's a very unpopular sort of rig. It's one of the best ones for spurious free dynamic range, and I use one of those remote controlled, and quite pleased with its performance. Pity they don't sell them anymore. You have to get a second-hand one. And then it sort of gradually gets worse. It's actually interesting that the nasty IC910 that everybody hates so much on transmit is not that bad on its receive SFDR. So it's just an antisocial radio. Going down, the FT991 it's amazing. Some of the newer things are worse than the older things. And you know, some of these are, you know, they're certainly usable. They're certainly usable, but they don't have the dynamic range that ideally you would like to have. So if you're going to try and get high dynamic range, you have to, at the moment, use a transverter and an HF transceiver. And in particular, you need to do this. You need to set the amount of gain in front of this system very carefully. You need to set it using an attenuator so that what you receive in terms of noise from the aerial in your quietest direction just raises the noise floor. Just increase the attenuator till you're at that point. Then your dynamic range will be as good as you can get. So that's what I recommend you do. And then on transmit, set carefully the drive level to the PA so that you're going to have a clean signal. So if you have HF transceivers and ideal transverters, which is possible, i.e. a transverter which is sufficiently good that the HF transceiver is the limit, then you can do quite well. The K4, which is quite rare at the moment, has a very carefully implemented dither on its A to D converter. And the measurements I'm seeing, like from the ARRL review, show it has the potential to get above 100 dBs SFDR, which would be impressive. I haven't measured it yet because I haven't managed to get my hands on one yet, but it's quite interesting. K3 we've talked about before. This is a K3, not a case in 3A, and there's a dB of penalty in that, and various other possible HF receivers. So you can get something that'll give you a really big dynamic range when carefully set up. So finally, transmit performance. We have a code of practice for contest operation. You can find it on the contest RSGB contest website. It's a link on the left-hand side, and it's worth reading. And in particular, for big stations, you need a pretty high level of cleanliness to avoid causing trouble to your fellow contesters. Amazingly, I work lots of people who have a big amplifier that they have bought from DX Shop or wherever, and they don't have a PEP meter. It is remarkable. And they say, oh, it's fine. Yeah, the needles are fine on this. Well, the needles on those or the bar graph displays do not measure PEP, I can assure you. I have checked. they underread hugely. They're like VU meters in audio. So if you want lots of overload, rely on those meters. I think anybody who has a big PA should buy a PEP meter. The best is just get a PEP converter for a bird through line. You can get the bird through line on eBay quite cheaply. You know, the cost is negligible relative to a PA, but if you have one and use it, you will really clean up the bands nicely. Find the point at which the gain is starting to roll over and never drive the PA to more than 70% of that level, and you'll get a clean signal without having to buy a spectrum analyzer to look at it. And you know, for contesting where, you know, we have to put things together out in the field, it really is the case that a big PA which is underdriven is the easiest way to keep a clean signal. Radiated noise, as I said, is a big problem, and it's actually getting a worse problem because of lower voltage rails used in modern transceivers. You need either minus 125 dBs on carrier per hertz of bandwidth for a small station, or minus 135 for a large station to meet the code of practice at 50 kilohertz offset. If you're a microwaver, you're allowed a little bit of latitude because, of course, you're frequency multiplying things, and that's why that's there. So here is a sample. It was a 2-meter trophy contest a few years ago. There's the band. This is measured in Oxfordshire, and in 444 hertz. It's an FFT display. The noise floor was minus 167 dBm per hertz, so pretty close to the noise floor you would expect. Lowest would be minus 173 if everything was perfect. But this is measured. And along comes this station. The noise floor's gone up by 10 dB, and it sounds like this. He's transmitting. He's not. He's back. You know, it's really, you really shouldn't do that. So, solutions. 1970s, IC202. The noise out of this is so good, it meets the code of practice limits for both small and large stations. PA6NL, when they were on, they used to use one of these driving an amplifier the size of a cupboard. And it absolutely fine signal. So that's the first thing, and so keep an eye out for those on eBay. Tuning's a bit sticky, but there you are. The 9700, if you're transmitting, you know, single aerial station, it does on 2 meters, provided the power's turned up to 85%, it does meet the small station limit, which is good. Unfortunately, if you use the power control to adjust the power, rather than use an attenuator in front of the PA, you turn the power down, the noise goes up, and so it goes outside the small station limit then. So generally, you need separate attenuators, don't rely on the power controls. And so in my little table for VHF, UHF transceivers, the only one that does meet the large station limit for a station in a box is that. That's the only one I know so far. So for large stations, you need the transverter approach. But you can do quite well. There are quite a few things that will do the small station limit okay. But just to show what you can do, this is measured data for a one of the ME2HT transverters and a case in 3A that comfortably meets the limits for both small and large stations. So it's well beyond. This is 10 dB per division here. So you've got plenty in hand with that. So conclusions. We have to hear stations despite unwanted signals. As I said, for the single aerial people, consider aerials with modest side lobes. provided you've got enough dynamic range in your receiver that you're not going to get overloaded by somebody nearby. And the reason we're using multi-array systems on large stations is just so that we can be heard all the time and just catch more of those stations who are on fleetingly. We need receivers practically with spurious-free dynamic ranges exceeding 100 dBs, measured in 500 Hertz, unless you happen to be in a really remote area with no strong signals to worry about, in which case you just concentrate on having a sensitive receiver. And for transmit systems, radiated noise less than -135 dBc per Hertz, which is, again, practical to do with the transverter approach. Again, unless you're located in a remote area with no stations who are going to be bothered, like nobody within a few hundred kilometres, then you can be a little more relaxed. But in IO 9192, we have lots of people close to us. And for simplicity, the transverter HF transceiver remains the simplest method. We are waiting for some better transceivers in a box. If we complain enough about them, we may get them. Thank you very much. Happy to engage in debate.
Thank you, Alwyn. Interesting as always. Now, anyone got any questions? All right, we'll start here with the easy one.
I have two questions.
Yep.
First of all, what do you think to the practice that we always used to do on contests of siphoning off some of the power that would go to the beam to an omnidirectional antenna to keep the frequency warm? Is that a valid?
It's exactly like my not very good side lobes antenna. But the point is that in the RSGB rules, if you're a small station, you're only allowed one antenna.
No, I'm talking about the 400 watt stations.
DF0MU, they used to have a stack of big wheels, and then a separate receive array.
Okay, I just wondered because we always used to do that years and years ago, and it still do.
It's a great approach.
Secondly, you mentioned operating contests. I operate from home. I'm in a bit of a dip. So troposcatter is quite reasonable because the horizon's less than 0.6 degrees generally. I do as well as expected, using 100 watts on 2 meters with an IC 9700. I've never, ever heard a station generating wideband noise at my station. Possibly the reason for that is I use an LFA, a 9 elements LFA, and I can hardly hear other people when they're not on beam. So that's possibly the reason why. But why have the contest committee not given dispensations for fixed stations in poor locations? Why is it applicable across the board?
That is a question.
That's not really an Alwyn question. That's a question to bring up tomorrow.
Contest forum tomorrow.
Wants to say something. You can talk to me tomorrow about that. Right. Okay. Yeah, Andy will host questions on that in the VHF forum.
Yeah.
There was another question.
Yeah. DR9A.
Hi, Alwyn.
Oh no.
Rob M0 VFC.
So sorry to hear that. Yeah.
Alwyn, you were talking about the relative benefits of stacks of shorter Yagis. Considering the mechanical limitations, where would you place the trade-off of if you can put a single beam higher versus a larger stack which gives you the better azimuth coverage, but mechanically you have to allow for a lower mast at that point? Where would you make that trade-off?
You get an enormous improvement in most sites by making sure you are very substantially above nearby clutter. I've measured, of course, the lower band you go to, the more it matters to get really high up into the air. Basically, you need a good, clear view, and if you haven't got that, you're wasting the aerial. So the first thing is to get things up high enough, and then think of the mechanical problems once you've got there. we've had our Gale Force 9 experiences. So yes, it's real. Oh, sorry, there was a Storm 10. Yes, that's true. So first thing, get the aerials up enough into the air, and then see what you can do at that height.
Any more questions?
Yes.
Well, Andy.
Andy.
I'll save you walking less. So it's just that. Thank you. You've covered most of what I'm going to cover in my talk later on this afternoon as well.
Oh,
with a
sorry.
slightly different spin, but that's, no, that's fantastic. A question. In situations where you've got one really strong signal on the band, I've come to the conclusion that perhaps blocking dynamic range is a more important parameter than SFDR, because actually your transmit signal performance is probably limiting a lot of the close-in intermod. Naturally, that often follows. But do you think that's a reasonable analysis or not?
I think that actually, I'm usually trying to hear something on a frequency, at least slightly different from the unwanted station. So I think blocking dynamic range, you've got to have it, but it's actually much easier to engineer, especially in an SDR, than spurious free. So, for example, if I'm put my radar hat on, then I scarcely even consider blocking dynamic range. It's a simple design parameter for the ADC, easy to achieve. So I tend not to talk about blocking dynamic range much because it's an easy engineering problem, whereas spurious free, because it can arise anywhere in the whole dynamic range of the converter, is far harder to engineer and is the one that usually causes the problems. That's my experience.
Cool. Thanks.
Any more? Last call for questions? No, none seen. Thank you very much, Alwyn. Always an interesting and educational talk. And can we thank him in the usual way?
As well as Andy's talk, can I advertise Sam's talk on VHF transverters tomorrow, 1:30, because maybe we should do a bit more transverter building.